This is the next video in the chapter on chemical bonding and molecular geometry. We are going to be using the pages from the packet I gave you that look like this and like this. So you can find that worksheet and follow along if you like. We are also going to be improving upon the table that we made in the last video. So I've gone ahead and pre-written the part that we already did, just so that this video doesn't take a million years to make. But I would highly recommend that you start a new page and pre-write this table along the left side, so you have the room to write or to draw all the other pictures we're about to make for molecular geometries. So we have just spent a whole video talking about electron group geometries, which included bonding pairs and lone pairs. And now we're going to indicate molecular geometry, which considers the shape made by the bonding pairs only. So let's write that out here. The electron group geometry that helps us describe how much space the electron groups take up. But we actually want to describe whether we care more about the shape made by the atoms. It's not that we don't like lone pairs. We do like them. We need to know where they are and we appreciate them, but they're not atoms. And when it comes down to it, we care the most about atoms. And so the name of the structure made by just the atoms is the molecular geometry. So let me show you what I mean in this example of ammonia that we've been talking about before. So remember that we have two types of electron groups. We have lone pairs, which only belong to one atom. And then we have bonding pairs, which connect atoms together, which connect two atoms. So when we named the electron group geometry before, we can think of that as encompassing the entire molecule. You can also think of that as being a better shaped circle. So the electron geometry includes all of the types of electrons, lone pairs and bonding pairs alike, whereas the molecular geometry that we're doing now only considers the electrons that connect to atoms together. So it's still the same shape, we're just going to be given a special name to this part of the molecule. And so we need to organize ourselves. So we're going to organize this table to look like the table we made before. So these are still our electron geometries along the side: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And what we're going to do is we're going to move down the line for each structure, and we're going to systematically remove one of the atoms from the picture and replace it with a lone pair. And then we're going to describe the name of that shape when it has 1, 2, 3, or 4 lone pairs in it, because we're going to be naming what the structure looks like when we don't consider the lone pairs in the shape. So we're going to make a big table, and I'll show you what each of these look like as we move across. So the first one is linear. Linear has 2 groups attached, and if we replace one with a lone pair, it doesn't need a name because it's just a single bond. So we don't need any of the boxes in this line of the table. Moving on to trigonal planar, there are 3 electron groups. So let's see what happens when we replace one of the electron groups with a lone pair. So I like to just draw the shape again with all 3 bonds and just draw a lone pair in for one of the bonds. So I remember that it's still there. I'm just not going to name the shape. So I want to name this part of the shape that connects atoms, and we call this shape bent. This is the shape that a water molecule has. So this is what a trigonal planar molecule looks like. And I'm going to use these extra hydrogens because I don't have enough lone pair models to represent what it looks like. So when we replace one of those atoms with a lone pair, the shape looks like bent. And so it is. Okay, so far so good. Moving on to tetrahedral. Tetrahedral has 4 electron groups attached. If we replace one of those electron groups with a lone pair, we get a structure that looks like this. We'll replace this one on the top. Keep these 3 atoms on the bottom. And you can see that that pyramid we talked about at the beginning is still there, with A as the point, and the 3 X's form a triangle-shaped base. So this one is called trigonal for the base, pyramidal, because it looks like a pyramid. And if we continue across and we replace a second X with a lone pair, we'll need to put in 2 into our picture, like so. We have 2 X's left, and we'll want to describe the shape made by just these 3 atoms. This one is also called bent. So there's 2 different types of bent. There's one formed from a trigonal planar electron geometry with a single lone pair, and there's one formed from a tetrahedral electron geometry with 2 lone pairs. So let's take a look at these. Here's our tetrahedral structure with 4 atoms on it. This one I have the proper lone pair piece. So this is supposed to represent a lone pair just chilling by itself. When we replace the first lone pair, it looks like a pyramid with a triangle-shaped base. And when we replace 2 lone pairs, we can see that we have a bent structure that looks similar to that first one. And again, there are still 4 electron groups. We're just naming this entire structure tetrahedral, and just the part of the structure with the atoms bent. All right, moving on to the fun groups. And when we have 5 electron groups in the trigonal pyramidal row, we're going to start by replacing the first group with a lone pair. And for these bottom 2 rows, it does matter which one you pick first. We'll talk about that more in the next video, but we are going to pick one of the equatorial positions to be the first position with a lone pair. And this is kind of a silly looking shape, but you can see that it looks a little bit like the axis with 2 legs on it, kind of like a picnic table. If you were to turn it to the side, it would look like a picnic table. This is called seesaw, because it also looks like the seesaw toy that we ride as a kid. If we continue to replace atoms with lone pairs, if we have 2 lone pairs, we are going to replace a second equatorial, and I'm going to change my mind and put it on this side, just so that the shape is more obvious. So we've got 3 atoms, 3 terminal atoms and 2 lone pairs. And now the shape looks like an axis with 1 leg, and it looks like the letter T. So this is called T-shaped. I guess they ran out of creative ideas for that one. And then we can replace a 3rd atom with a lone pair. Yes, molecules like this do really exist. We can replace all 3 of those equatorial atoms with lone pairs. We just have 2 terminal atoms left, and we can see that this shape looks familiar. It looks just like our linear structure. So there are 2 ways that we know of to make a linear structure. a central atom with 2 terminal atoms, 2 electron groups, or a central atom with 5 electron groups where 2 of them are atoms and 3 of them are lone pairs. And then we don't have a picture for this one, because if we continue to take away, all we have is a single bond. So we should mark off these ones that we don't have as well. Empty slots. Okay, so here's our trigonal bipyramid. It has the 2 terminal atoms along the axis and that triangle-shaped plane of 3 around the middle. When we start to replace one of those groups with a lone pair, we only have 2 things around the middle, and if we turn it on its side, you can kind of use your imagination to see how it might look like a seesaw with 2 little kids riding back and forth on these 2 sides. Doesn't stand very well, though. If we were to replace 2 of those groups with lone pairs, there's our T-shaped structure. This looks more like a T if we turn it this way. And finally, if we replace 3 of those atoms with lone pairs, you can see that it's a linear structure. You can still see where those lone pairs are attached around the middle. They form sort of a triangle-shaped plane. But if we were to name just the part with the red and black atoms, this shape is linear. Okay, we've got one left. Let's move the screen up a smidge. There we are. So our last one is 6 electron groups, which is octahedral electron geometry. So when we replace the first atom with a lone pair, I am just going to choose this one. It doesn't actually matter which one we choose. So I'm going to choose the one on the bottom so that my picture looks the nicest. So in this structure, we can see that we have 4 atoms that are in the same plane. And then we have 1 point on the top. And if we connect them, we can see that this shape looks like a pyramid. Remember that this looked like it had 1 pyramid on the top and 1 pyramid on the bottom. But this time the base is a square instead of a triangle. So this shape is called square pyramidal. The names really do make sense if you draw the picture correctly. If we replace a second atom with a lone pair, we're always going to choose the lone pair that is across 180 degrees from the one that we chose first, no matter which one we chose first. So I chose the one on the bottom first, so I need to choose the one across from it on the top to replace second. This one is probably my favorite structure because now all we have left is the square plane. We no longer have either of the atoms on the axis. So this shape is called square planar. We can keep going. We can replace 3 of the atoms with a lone pair. And remember, even though some of these 6 attachment points only have lone pairs in them, we are still drawing all 6 bonds to remind us that there are still 6 electron groups. So at this point, it doesn't matter which one I choose, so I'm going to pick that back left one. And we can see that there's a familiar shape being formed here. If you squint and you cover up all of the lone pairs that we don't care about, you can see that this shape has an axis and a single leg, just like this one up here with 5 electron groups and 2 of them lone pairs. So this one is also called T-shaped. There's 2 different ways to form T-shaped. And we can keep going. We can replace a 4th group, the 4th atom with a lone pair. If you can fit it on your paper, which we'll see if I'm able to. So 1, 2, 3, and of course now we have to pick the one across from it, 4 lone pairs, and 2 bonding pairs. Make 6 electron groups, and if we name the structure that only has atoms in it, it should look like a line, depending on your drawing ability. So now we have a third way to make linear. We have 6 electron groups with two terminal atoms. We have 5 electron groups with 2 terminal atoms. And we have 2 electron groups with 2 terminal atoms. So let's look at our models here. Here's our octahedral with 6 atoms. We've got the axis, and then we've got that square plane around the middle. When we replace the first group to make the pyramid, it looks like this. So you can see there's the point of the pyramid, and here's the square plane that makes up the base. And I'm afraid I have run out of green, so we are going to have to switch to blue atoms, unfortunately. When we replace both the top and the bottom of the octahedral structure, we just have the 4 atoms around the middle. So it looks a little bit like a Ferris wheel. And we call this square planar because these 4 terminal atoms are all in the same plane. If we replace 3 of the electron groups with lone pairs, we end up with T-shaped. And you can see that here. We've replaced the top one, the bottom one, and the one on the side. And now we have 3 of the equatorial ones left. If you hold it at this angle, it looks like a T shape. And finally, if we go all the way to extremes and we have 4 lone pairs, we just end up with a linear structure where we've replaced the top, the bottom, the back, and the front. We just have 2 atoms across from each other to get a linear structure. So that is a lot of variations of octahedral. So finally, just a reminder, in this mega table that we have made, remember that this first column where there are 0 lone pairs and all of them are atoms, this is the electron group geometry. This just describes what the structure looks like for the lone pairs and the bonding pairs. But when we want to describe just what the shape of the atoms is, that's when we use the full table. So there can be some atoms where all of the electron groups are bonding pairs, where octahedral may describe its electron group geometry and its molecular geometry. But if you have a combination of lone pairs and bonding pairs, you're going to need to use one of the names from the center part of this table. So I hope you have enjoyed 15 different models made from my model kit, as well as some pictures. I would encourage you to practice drawing these pictures on your own so that your pictures actually look somewhat like they're supposed to. And in the next video, we will talk about how these shapes are distorted slightly in reality under certain conditions.